Okay, enough of the legal stuff. Let's get back to some engineering, right? So we have a toolkit that we use. So if we're doing sequestration projects, we have this toolkit, and we've talked a bit about legal and permitting, but I want to touch on just briefly some of these other things that we use to move projects along from site selection through characterization to the design, permitting, and operations. So I'm going to just touch on a couple of these so you could see what's in our toolkit as engineers. So first up is MVA, so again, monitoring, verification, and accounting. And I'm not going to go through these in any detail, but when you're managing a project, what it's telling you is when you design these monitoring programs to get a permit to operate, you're covering an enormous range of techniques. So you've from atmospheric monitoring, satellite imaging, collecting gas samples which get analyzed in various spectroscopic techniques, geophysical techniques to just drilling a well, pulling water samples up and analyzing them. So you have to be able to have a grasp, not maybe the very detailed knowledge about the limitations and scope of each of these techniques, but you've got to have some idea about what each of these techniques can do for you when you're designing a monitoring program for a sequestration project. In terms of sequestration system design, this is a part where our engineers, we get involved in very detail, because what we want to do is link the properties of our reservoir. So we want to inject CO2 at some pressure and mass flow rate. And so in order to do that, we need to design our injection wells such that we don't have a high pressure drop through the well such that the CO2 it won't be able to be injected. But we don't want to make it too big, because as the injection well gets bigger, our costs go up, our materials costs go up, everything goes up. So we want to be able to hit that sweet spot in terms of sort of the minimum dimensions that are needed to support the mass flow rate for a particular project. So after we design the well, then we can provide those pressures and temperatures and mass flow rates all the way back to the power plant or industrial facility, whatever it may be. Tell the engineers, okay, when you're capturing CO2, I need you to supply that at given pressure, given temperature, given mass flow rate. And oh, by the way, as we go through some seasonal variations, that will affect what those pressures and temperatures are that we need to have coming out of the plant. So to do that, we use a tool. I call this thermal hydraulic modeling. So all you're doing is segmenting the infrastructure from the plant gate through the pipeline to the wellbore and then down to the injection reservoir. And you're calculating pressures, pressure drops along the way, what's the internal energies, and so taking into account frictional losses, the gravity heads, acceleration, all those things you need to do. And you have this nonlinear equation of state properties for CO2 that you have to account for along the way. So why is this important? Because that's how much it costs to run pipeline these days. And so if you're talking about a project that may have a 5-mile pipeline from the plant to the sequestration site, if you blow it, so you say you specify an 8-inch pipeline, but you really only needed a 6-inch pipeline, you've just cost your project about $10 million by making that mistake. So you really need to do this right in order to get the capital cost for the project where it needs to be.